Hi folks, I'm going to begin the week 13 recitation problems from 16.4. I've shared those in the chat and I'll try and mirror them right now. So 16.4 deals pretty exclusively with writing parametric equations and changing between variable systems here. You're going to use some of these techniques in 16.5 as well. So we'll just jump into number one, find a parametric representation for the surface. So we're looking for the part of the elliptic paraboloid that y equals 6 minus 3x squared minus 2z squared. That lies to the right of the xz plane. All right, so I've copied that problem over to the whiteboard here. Let's see if I can switch. Nice. Okay, so the language in this problem maybe could be a little bit better when we say the right of the xz plane. We can imagine that the x-axis is pointing out towards us, the y-axis to the right, and the z-axis going up. So the xz plane would be coming sort of straight out of the board towards us, and to the right would be positive y values. So to the right of the xz plane, that really just means y is strictly greater than 0. Okay, so here's our surface. We have x, y, and z. And the first thing we're going to do, because it's already written in the form y equals, is write representations for x, y, and z strictly in terms of these variables x and z. And the easiest ones are going to be x and z. They'll just be themselves. So our new x value will be x. Y will equal 6 minus 3x squared minus 2z squared. And z will equal itself. And depending on the problem, if we have the function represented with a different variable solved, we can use a different parameterization. We're going to see some problems where we're given other variables that represent a surface. But usually, if we have a single variable that's been solved for in terms of the other variables, we'll choose to represent that in terms of those two variables. So we've pretty much finished the problem here. We're just going to write our parametric equation now. R of x and z will output the vector x, comma 6 minus 3x squared minus 2z squared, comma z. Right, so that vector. And one more thing for us to do, we do have a restriction on the domain for y, and so we'll have to translate that into the variables x and z. Happily, it's a pretty straightforward inequality here. So y being greater than 0, we'll just change that to 6 minus 3x squared minus 2z squared is greater than 0. And we're done with the problem. So problem 2 asks us to represent a cylinder x squared plus z squared equals 1 between the planes y equals -1 and y equals 3. So I've copied that onto the whiteboard here, and our goal is just to represent that in terms of really any two variables. So I think good choices here, since we have a restriction on y, we could let y be itself, right? We could represent y as y. And we want to represent x and z as well, ideally using a single variable. So one way to do that would be to consider a polar representation out of the xz plane for x and z. That representation would be as follows. We want x to equal sine theta and z to equal cosine theta, right? And we can verify then that sine squared plus cosine squared equals 1. There may be more than one representation that we could use here as well. And then we'll let y equal itself. And now we have representation for all rectangular variables in terms of theta and y. So then our representation would be vector valued function r of y and theta will output the vector sine theta, comma y, comma cosine theta. Okay, so we have y and we have theta. We want to represent domains for both of those variables. So theta can go from 0 to 2 pi. And how about y? Well, y, we have restrictions on already. So y will vary between -1 and +3. And we are done. So I just realized that I had mislabeled those problems. That was 1A and 1B, and we're now on to 1C. 1C asks us to represent the part of the plane z equals 5 that lies inside the cylinder x squared plus y squared equals 16. For problems like this, it is useful if we can visualize them geometrically. That may help us to decide on the right parameterization. Really what we're talking about here is a disk, right? Because x squared plus y squared equals 16. That's a circle centered at the origin, or actually, sorry, it's a cylinder centered at the origin with radius 4 extending upward parallel to the z-axis. So the intersection of that cylinder with the plane z equals 5 would be a circle. And it would be a circle centered at 0, 0, 5 and of radius 4. So I'll pause that and we'll go back to the whiteboard. So let's see, how can we represent this one? We can, sorry, give me one sec here. So if z equals 5, we have x squared plus y squared equals 16. Something with a circular geometry that has that sort of symmetry to it. A polar equation is often a good way to represent it. So we could do the following. We could represent x as r cosine theta. Okay, so r is the radius, theta is the angle. Y equals r sine theta. And z just equals 5. Okay, so the reason we couldn't just use x and y here, we do have just two variables for the representation of the surface, but we do have this z equals 5, right? So we'd have to translate that into some sort of restriction on x and y, and that won't work. We can't do that. However, when we represent these in terms of r and theta, we can set domains for those two variables that will do the trick. So now our function r is given by, probably shouldn't reuse that. I'm going to use a different variable. Let's call it j. Why not? So j of r and theta outputs the vector r cosine theta, comma r sine theta, comma 5. And then we'll just translate the restriction here. So we want theta to have a full circle, so we'll let theta vary between 0 and 2 pi. And to get the full interior of that disk, we want a radius starting at 0 and ending at 4, right? Because the radius of this circle is 4. And we're done. Okay, so here's the real problem 2. Problem 2 gives us some sort of surface where x is represented by u squared, y is represented by u minus v squared, and z is represented by v squared. And what we want is the equation of the tangent plane to that surface at the ordered triple 1, 0, 1. So we've been provided these parametric equations, but you can also picture a problem in which we did just what we did in problem 1. We created parametric equations and then did something like this. So let's start by taking this ordered triple 1, 0, 1 and solving for u and v, like what u and v values correspond to that. So if we want x to equal u squared, so we want 1 to equal u squared, that would mean that u could either be +1 or -1. And if u is +1, and we'd subtract v squared to get 0, well then v squared must also be either 1 or -1. So we actually get more than one possibility for u and v here. However, our equation for y needs to equal 0, so we can exclude the possibility that u equals -1. We have u equals 1, and v could equal either positive or -1. So really we have two ordered pairs here. uv equals 1, 1, and also 1, -1. And we'll come back to that a little bit later. So now I'm going to write that function r. I mean, the components have been provided to us, but we're going to use this function in a moment. So r of u comma v gives us the vector u squared, u minus v squared, comma v squared. And so our general strategy to find this tangent plane is going to be to go to that point, to find two tangent vectors at that point and take their cross product, which would give us a normal vector, and then use the equation of the normal vector to create the equation for our tangent plane. So let's see, what do we need to do then? Well, we need two tangent vectors at that point. And so the easiest way to do that would be to take partial derivatives in the direction of u and the direction of v. So we'll take r sub u and r sub v. Okay, so partial derivative with respect to u would give us the vector 2u comma 1, right, because negative v squared we treat as a constant, comma 0. So there's our derivative in the direction of u. And partial derivative with respect to v, we'd have 0, negative 2v, and positive 2v. Right, so here are two tangent vectors. We're going to take their cross product to find the normal vector. So for this problem, I will show all the details of taking that cross product. So our normal vector, and in the book they use the variable n in a way that is a little bit different from the way they've used it in previous chapters. N could have really any magnitude, so we might normalize it later, but n could have magnitude other than 1. So the normal vector will be r sub u crossed with r sub v. And so I'll write out our determinant here. We got I hat, j hat, k hat, and we have 2u, 1, 0, 0, negative 2v, and positive 2v. Sorry for writing really small there. Hopefully you can read that. Okay, so in the direction of I, we have 2v minus 0. So we just have 2v. In the direction of j, it's going to be negative, and then we have 4, I can't even read what I put there, that's 2u times 2v minus 0. So given the negative sign there, we'll have negative 4uv. And then for k, we're going to have 2u times negative 2v minus 0. So negative 4uv as well. Okay, so here's something important. We have these two different representations for our point, 1 comma 1 and 1 comma negative 1. If we plug in 1 and 1, we get the vector 2, negative 4, negative 4. If we plug in 1 and negative 1, we get 2, 4, and 4. What's important is that those are parallel. Okay, so good. That's good news for us. All right, so let's evaluate the point there. I'll just do exactly what I said there. So our normal vector evaluated at 1 comma 1 or 1 comma negative 1, doesn't really matter which one we use, is going to give us the vector 2 times 1, so 2, negative 4, negative 4. And so then the representation of our plane, the easiest way to do that would be to use these as coefficients and basically to use like the point slope equivalent. So we'd have 2 times x minus 1 minus 4 times y minus 0. I'll write it out like that, y minus 0, plus negative 4 times z minus 1. And this whole thing equals 0. So here's our final answer for that tangent plane. So just to finish up this point here, if I'd used our second ordered pair for u and v, I would have gotten negative 2, positive 4, positive 4, and that would give us the exact same equation, just multiplied by negative 1, and since it's equal to 0, that doesn't change our answer for the tangent plane. All right, back with problem 3. We're given the surface in terms of u and v, where x equals u plus v, y equals u cosine v, and z equals v sine u. And we're going to find the tangent plane at the point 1, 1, 0. So just like in the last problem, we want to represent that point in terms of u and v. I'm not going to show solving that system of equations, but you could solve basically for u in terms of v and then do a substitution. You actually have 3 equations here and 2 variables, so it shouldn't be too bad here. So u comma v, if we want this to equal 1, 1, 0, what we'll do the trick is letting u equal 1 and letting v equal 0. And we can just confirm that that works here. So 1 plus 0 does equal 1. 1 times cosine 0 equals 1. And 0 times sine 1 equals 0. Okay, so good. So that works. And let's see here. So what do we want to do? We want to, again, find tangent vectors at that point and cross them to get our normal vector, and then we'll use that to find the equation for the plane. So let's take some partial derivatives here. We'll take r sub u. So partial derivative with regards to u will give us 1. And let's see, we're treating cosine v as a constant. So a constant times u, its derivative would be that constant. So cosine v. And then the derivative of v sine u in terms of u would be v cosine u. Okay, so there's one of our partial derivatives. And in the direction of v, we'll have 1. Let's see, so derivative of cosine is negative sine, so negative u sine v. And then differentiating here with respect to v, we will have sine u. Okay, so then our normal vector, n, is going to be the cross product of those. So r sub v, r sub u, crossed with r sub v. Let's see, we have 1 cosine v, v cosine u, 1 negative u sine v, and sine u. Again, apologies for the small writing here. Okay, so when we do that, our cross products can be a little bit complicated, but we'll be able to plug in the values for u and v. If we wanted to, we could actually do that now if all we want is to find our normal vector evaluated at that point. But I'll show it in its detail here. So let's see, maybe I'll write it down here so we don't run out of space. So we're going to have I times cosine v sine u. So cosine v sine u minus negative v squared cosine u sine v. Or sorry, it's not v squared, it's minus u times v. So plus u v cosine u sine v. Okay, so there's our x component. Our y component, we have these 1s in the column here, so that's nice. We'll have sine u minus v cosine u, and then j hat's made negative there, so we can write that as v cosine u minus sine u. And our last component here for k, again, we have a nice column here, so 1s will have negative u sine v minus cosine v. Okay, so we're going to evaluate this normal vector at u equals 1, v equals 0, just to save a little bit of space. I'm going to do that up here. Right, so our normal vector evaluated at 1 comma 0. We'll just go term by term here. So we're letting u equal 1 and v equal 0. Okay, so sine of 1 times cosine of 0. Cosine of 0 is just 1. So here we have a sine 1. And then over here, we have sine of 0. So this whole thing is going to go to 0 here. We also have u and v. So anytime we see a v, that whole term is going to cancel here. So our vector then, the x component will be sine 1. And let's see here. So v cosine u, v is 0, so that'll go away. We have negative sine u, so negative sine 1. Sorry, I'm running out of space here. I'm going to move the camera over just a little bit. There we go. And then finally, our z component, let's see, we have negative u sine v. So again, sine of 0 is 0, minus cosine of, is that cosine of u or cosine of v? I'll make sure I got this right. That should be cosine of v. Okay, so minus cosine of v. Well, cosine of v, that's cosine of 0, so that's 1, right? And then negative u sine v. Sine of v will be 0, though, so we'll have a negative 1 here. So there's our normal vector evaluated at u equals 1, v equals 0, sine 1, comma, negative sine 1, comma, negative 1. So that's a normal vector valued at that point. And now to finish our plane, we'll use those same coefficients. So we will have, let's see, our point is x equals 1, so we'll have sine 1 times x minus 1 minus sine 1 times y minus 1, and then minus 1 times z minus 0 equals 0. And there's some simplifying that we could do here. I think we'll just leave it in that form for now. Okay, here's our fourth and final problem. This one's a little bit different. We want to find the area of this surface, z equals x plus y squared, that is above this triangle that has vertices 0, 0, 1, 1, and 0, 1 in the xy plane. So one thing that's important to this problem is that the surface is smooth, right? It's differentiable. There's no sorts of discontinuities in the region that we're looking at here. And what that allows us to do is to use a formula actually from 16.4. The derivation is in your book if you're interested. So here it is. So the area of some surface S is going to equal a double integral, right, over d of the magnitude of the normal vector, right, using our parameters u and v, times dA, or if we're using u and v as our parameters, that would just be times du and dv. Okay, so that's a special formula for area. It's in the books, and for this problem, it's appropriate based on the continuity of that surface. So in the previous problems, we were using the normal vector to create the equation of a plane. We can think of this problem as just another application of the normal vector. Now, the formula that I wrote here uses u and v just to emphasize that this works for different parametric representations of the surface. For this one, since we have z in terms of x and y, we can write our parametric equation for x, y, and z using the existing variables x and y. So that's the first thing that we'll do here. We'll write our function r of x and y will yield the vector x comma y comma x plus y squared. Okay, so now we'll go on to find those tangent vectors using partial derivatives. So in the direction of x, we will have 1, 0, comma 1. Our partial derivative with respect to y will give us 0, comma 1, comma 2y. So we've done a bunch of cross products already. I'm not going to show all the details here. But our normal vector then is going to equal, let's see what we have here. Will give us, cross product will give us, I think, should be 1, comma, let's see, negative 2y. Oh, negative 2y. And then our z component will be, let's see, we have 2y minus 0. So 2y, I think. Let me check that. Oh no, sorry. Our z component will just be 1. There we go. It's 1, 1 minus 0. Okay. So here's our normal vector, 1, negative 2, y, 1. And what we're going to do here is just take the magnitude of that vector, and we'll be close to done with the problem. And of course, because I tried to be quick and not show all the steps, made a small mistake. That should be negative 1 here. Okay, so the magnitude of the normal vector then is going to equal the square root of negative 1 squared plus negative 2y squared plus 1 squared. So the 1 squared and the negative 1 squared, we combine that to 2 plus 4y squared. So there's the magnitude of n. So let's set up our integral here. We have a double integral, and we're going to evaluate it in terms of x and y. And the secret here, based on the triangle that we want to represent, is to vary x between 0 and y, and vary y from 0 to 1. So we'll go in the y direction from 0 to 1, and the x direction from 0 to representation y, and our integral is going to be of 2 plus 4y squared dx dy. Right, and doing it in this order makes it a lot easier, right, to do this integral here, because we'll have a y that shows up and helps us. Okay, so since we don't have any x's here, that inner integral is going to be pretty straightforward. It's just this constant times x evaluated at 0 and y. So we would have our constant 2 plus 4y squared times x evaluated at y and 0. Well, if x is 0, the whole term disappears. And if x is y, we'll just have this as our remaining term when we go on to our second integral. Okay, hopefully that wasn't combining too many steps here. So next, we can evaluate our integral in terms of y. And luckily, evaluating in terms of x first introduced our variable y that we need to complete this integration. Okay, so just because we're running out of room, I'm not going to show all the u substitution steps. But if we imagine our antiderivative as being something related to 2 plus 4y squared to the 3/2 power, we can imagine what coefficients we'd want here. So let's see, we'd have 3/2 that would come out in front, and then we would also have an 8y that would come out in front. So we'd have 3/2 times 8y. That would be ideal for what we have here. So 3/2 times 8 would be 24/2. And so to put that there, 24/2, that's just 12. I can put a 12 here and a 1/12 there. And then I have exactly what I need for my integration here. And so what that'll give us is an antiderivative of 2 plus 4y squared raised to the 3/2 power. And we're going to evaluate that at 1 and 0. And so evaluating that at 1, we get 2 plus 4 to the 3/2. So let's see, 4 to the 3/2. 4 to 3/2, that would be, I think, just 8, right? Let's see how we have. Sorry, I forgot our fraction here. We have that 1/12. Okay, and so we have 2 plus 4 times 1 squared to the 3/2. So sorry, that would be 2 plus 4 is 6 to the 3/2 power. So 1/12 times 6 to the 3/2 minus plugging in y equals 0, that would be 2 to the 3 halves. So both of those are irrational, so it's okay to leave them like this. Or if you prefer roots, this would be 1/12 times 6 root 6, I think. Yep. And 2 root 2. And we're done. So hopefully these problems were helpful. I know in section 16.5, we'll be doing some integrals that have a similar setup or that involve the normal vector as well. If you have questions, leave them in the discussion forum of D2L. I will check the YouTube comments, I guess, but I look in D2L first. All right, see you guys soon.